Also tonight we're here because of the Friends of Mount Tam and the San Francisco Amateur Astronomers. I hope you're meeting some of them later after the lecture tonight and after the star tour, because their telescopes are set up down at the Rock Springs parking lot. Following our presentation tonight, we'll have a sky tour by the urban astronomer Paul Salazar. Sal is doing crowd control right now. Paul will jump in after we hear from Dan Werthimer. Dan is one of humanity's great explorers. For almost 40 years, his form of exploration has been SETI, the search for extraterrestrial intelligence. Dan is the leader of several UC Berkeley SETI efforts, including the world-famous SETI at Home project. Dan has written extensively about SETI and has lectured all around the world. Years ago, Dan was also a member of a notorious group called the Homebrew Computer Club, which had members like Steve Jobs and Steve Wozniak. Dan claims that he's the only member of that club that failed to become a millionaire. Please welcome Dan Werthimer.
Thanks very much. I wanted to talk about this question, are we alone? Is anybody out there? And you probably know the field called SETI. SETI is the search for extraterrestrial intelligence. I want to talk to you about this question, are we alone? Is anybody out there? And some of the early ideas, Carl Gauss, 200 years ago, suggested that we get in touch with ET with a large geometric structure on the Earth, a big triangle on the sky made of pine trees, a big square of dirt, big square of wheat, big square of water, and ET would look down and see that we knew about the Pythagorean theorem. And it was a clever idea. Unfortunately, it was not funded. And then von Littron, also a couple hundred years ago, suggested that we get in touch with ET by digging a circular ditch 20 miles across. So von Littron suggested that we dig a circular ditch and fill it with kerosene and use this match, not to scale, to make a bright ring of fire. And ET would see this bright circle of light with their big telescopes and then get in touch with us. Unfortunately, it met with a similar fate. It was not funded also. And then Charles Crow suggested we get in touch with the Martians by reflecting sunlight using very large mirrors to the Martians, one where he lived in Paris and the others to outline the shape of the Big Dipper. It was also not funded. The first funded project was to send pornography into space. This was the plaque on the Pioneer 10 spacecraft that was launched in the 70s. This is the solar system and the sun and Mercury, Venus, Earth, and the spacecraft. These are directions to pulsars so ET can find out where we live in case they want to come and eat us. So that was the first funded project. Then came a theoretical way that you could calculate the number of civilizations in the galaxy called the Drake equation. And the Drake equation is the number of civilizations we could communicate with us, and all you have to do is multiply all these numbers together and you could figure out how many civilizations. Unfortunately, we have no idea what any of these numbers are. So you can't really do it theoretically, you have to actually go out and look. Some of the factors in the Drake equation are how many planets there are, how many planets have the right environment for life, how many, if you get life gets started, how many do you get intelligence, eyes for intelligence? And some of the last factors are, if you get intelligence, do you get communication technology? And the last factor is, if they get communication technology, if they can talk to us, this L is how long do they live? Our star is about 5 billion years old. It's going to last another couple of billion years. Some stars are 10 billion years old, so there may be very advanced civilizations out there. One of the factors in that equation was how many planets are there. And if you had asked astronomers 20 years ago, are there planets going around other stars, we would say we think so, but we really don't know. That's all changed, you probably know. Now we know about that most stars have planets going around them. One of the ways you can detect a planet going around a star, it's too small to see directly even with the best telescopes. But when the planet goes around the star, it pulls on the star a little bit, and the star wiggles as the planet goes around. And if you see a wiggling star, it doesn't wiggle very much. It just moves at walking speed. But finally, astronomers can detect those wiggling stars, and that tells you there's a planet going around. Here's a star that's wiggling. Actually, it's wiggling slowly, and it's wiggling fast. Do you know why? It might have two kinds of wiggles, a fast wiggle and a slow wiggle. Two planets, right. So this one's actually got multiple planets. The new way to find planets was done by this thing called Kepler that NASA launched, this satellite called Kepler. And I don't know if you can see this little black dot. That's a planet going in front of a star. And when the planet goes in front of a star, it dims, the starlight dims just a little bit, not by much, maybe a part in 1,000, because the planet's a little dinky thing. Anyway, what Kepler did is it stared at about 100,000 stars, and occasionally a planet would go in front of one of them. And because the telescope's in space, it can sense these very minute changes in the brightness of stars and figure out when the planets go in front of them, called an occultation. And it found the very first rocky planets, and now it's found many planets. And extrapolating on the planets that it's found, it looks like there's 1 trillion planets in the Milky Way galaxy. That's more than there are stars. There's about maybe 1/5 of a trillion stars, but there's 1 trillion planets in the Milky Way galaxy. A lot of them have multiple planets going around them, and now we know that some of them are rocky and some of them have liquid water. So we think there's going to be about a lot of places for life. And there's a big announcement coming out on Monday that you'll see on the front pages maybe about how many planets are suitable for life. There may even be life in our own solar system. This is a moon going around Jupiter called Europa, and it has liquid water. It has a big ocean. Unfortunately, it's covered with ice. This white stuff is about 50 miles of ice. And I ask a lot of kids, I give talks to kids, I ask them, we want to figure out if there's something swimming around in this ocean. How can we figure out how to get through this ice? And the girls, well, the boys, they all say use machine guns or bombs. The girls are a little more imaginative. They say melt your way through, or use mirrors to reflect the sun to melt your way through or something. But the boys usually think of some kind of violent technique. So we don't know how life got started. Maybe in something like this, the primordial soup. And people have done experiments where they simulate the early atmosphere. This is what was going around on Earth. There was some methane and ammonia and hydrogen and water. And they put all that stuff in a flask, and then they simulate sparks they make sparks to simulate lightning that we know was around in the early atmosphere of Earth. And you don't get gorillas crawling out of this thing, but you do get the basic building blocks of life, the amino acids and the things that you and I are made of. So we're beginning to understand how life gets started on Earth, and it started very early. We know, like, the oldest rocks you can find have signs of life on them. So the fact that it happened quickly here on Earth makes us think that it may be a common process. And we think that a lot of planets are going to have simple life forms, bacteria. It's probably, intelligent life is much more rare, but there's probably going to be a lot of simple life all over the galaxy. So if there is life in the galaxy, how are we going to get in touch? So one of the ideas is that Earthlings send off radio and television out into space, and maybe ET does that too. And this is a plot of television power leaving the Earth as a function of time, 1940, 1950, 1960. And you can see we're getting brighter and brighter, growing exponentially. We're brighter than the sun now at television frequencies. And so the early shows that left the Earth, like I Love Lucy and Ed Sullivan, they left the Earth about 50 years ago. And so they've now gone out traveling at the speed of light, about 50 light years. They've gone past about 10,000 stars already. The nearby stars have seen The Simpsons. So you can turn this around and you could say, okay, if we're polluting space with all our radio and television and radar, maybe ET's doing that too. And so we've even sent messages on purpose. This is a message that consisted of a sequence of zeros and ones. And if you turn the zeros and ones into black and white squares, you see the solar system and a human and DNA and amino acids and a radio telescope. So we pollute space with accidental messages, radio and television and radar. So we can look for artifacts of their civilization. Maybe they're not intentional. They're just like our radio and TV. Or maybe if we're lucky, maybe they'd send us a deliberate message. Maybe they do want to communicate with us with a laser or radio signal or something like that. And if they send us an intentional message, they'll probably make it easy to decode, maybe some pictures and language lessons. And they might send us a huge amount of information, their whole Library of Congress, all their music, poetry, literature, science, medicine. Maybe they'll tell us how to get on the galactic internet. Maybe they'll tell us about the million other civilizations they've been talking to. So we could learn a lot. So I'm not the first guy to think of this. The early radio pioneers, Tesla and Marconi, they both actually went looking for radio signals from ET. In fact, both of them thought they had found signals. It turned out they were listening to distant lightning. They call them whistlers. They heard that whistling noise and they thought they had found ET, but it turned out it was just lightning that was thousands of miles away. And then more modern searches done in the 60s and 70s. And now there are several groups doing this. There's a group in Australia, there's a group in Argentina, there's a group in Italy, and so a group at Harvard. We use these big radio telescopes. This is a telescope that's 300 feet across. And we want to do that. We use these big telescopes because it's just a big radio antenna. We think the signals are going to be very weak by the time they get here, traveling hundreds of light years. And so this thing, it's like a big mirror. The radio waves come down and they come to the receiver here at the focus. They bounce off this mirror and they come to the receiver. While we were using this telescope looking for ET, this is what happened. And you might ask, how did that happen? And the answer, according to the World Weekly News, is that the aliens did not want to be discovered and they zapped the telescope. And that is an actual interesting idea because this is another telescope that while we were using this telescope, this is what happened to that telescope. So maybe they've zapped it twice. So now we're using this, the world's largest telescope. This so far has not been zapped by aliens. This is 1,000 feet across. It holds 10 billion bowls of cornflakes. It's in Puerto Rico. It's called the Arecibo Radio Telescope. And you might have seen it in a James Bond movie called Contact. I'm sorry, in the James Bond movie called GoldenEye. It was also in Contact with Jodie Foster, but in GoldenEye it comes up out of the water. It doesn't really do that. It was also with the Jodie Foster in the Contact movie. And the radio waves get focused. Let me see if I can go back to this slide. They get focused, they get reflected by this giant mirror 1,000 feet across up to the receivers at the top. And the receivers at the top can move around and track the stars. And we figured out a way to use this telescope all the time, that whatever astronomers are doing, whatever they're pointing to, a galaxy or a star or a planetary system, we're always looking, surveying the sky, looking for ET. So we're using it almost 24 hours a day, all year round. We have a group of about 20 people. We get funded by the National Science Foundation and NASA and individuals that help us out and companies that donate some of the equipment we use. And we have different telescopes. The one I just showed you, the Arecibo telescope. We also use one in West Virginia. We're using one in the Netherlands. And we're using some infrared and visible telescopes too to look for laser signals. And we have a bunch of different searches at Berkeley, some looking for radio, some looking for laser signals at visible, some looking for laser signals in the infrared, looking for different kinds of signals. The first search that we did was called Serendip, and it was funded by NASA. NASA requires that you use acronyms. So Serendip is the search for extraterrestrial radio emissions from nearby developed intelligent populations. Tucker Hyatt, our host, worked with us on Serendip, and also worked with us, I think, on the early days of SETI at home as well. This is one of the problems in looking for ET is that we don't know what frequency ET might be broadcasting on. So we want to listen to many, many channels or many, many different frequencies. So this is channel number 2,264,191. This is channel number 2,264,959. And here's a strong signal at one of those channels. That's the kind of thing that we're looking for. And this is another kind of signal that we're looking for is a drifting signal. It's and those are pretty easy to see with your eye. They might be drifting because the planet might be spinning around, introducing a Doppler drift, or maybe going around its star. We don't know how fast it'd be drifting. But the problem is we have about 100 million of these things to look at every second. So we need a lot of eyeballs looking for these kind of drifting signals. Another kind of thing we look for is a pulsing signal, a bip, 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 bip. And that's hard to see with your eye. But here I've circled them for you. So we could have 100 million eyeballs looking at these things, people all over the planet, but we also can do it with computers. And what we did is we stored the data and we sent it out to people around the world who use a screensaver program called SETI at Home. Are any of you running the SETI at Home screensaver? All right, a few, thank you very much. And so you can download this program. It's a free program. You go to the SETI website. You can download this, install it on your home computer or at school or at work or your laptop. We can now make it run on cell phones. If you have a cell phone, you can run SETI at Home. Anyway, what it does is everybody gets assigned a different part of the sky. So you'll get one part of the sky, you'll get another part of the sky, you'll get another part of the sky, and you get something called a work unit. And it wakes up when you go out for a cup of coffee, your screensaver pops up, but instead of just putting pretty pictures on the screen, it's actually combing through the radio spectrum looking for interesting signals. And here it's found something sort of interesting. And after it's finished going through all the data that you've been assigned, it sends the signals back to our server in Berkeley. And if you're the lucky one that finds that distant murmur of a civilization, you get the Nobel Prize. This is what it looks like when it's running on your screen. It has your name and the coordinates, where you're looking in the sky, and it shows you the best signal. And then it just keeps on doing this. And then when it's done, it'll get a new work unit. You just keep doing that until you find ET. The problem is the Nobel Prize is about $1 million. There are 8 million people who are running the SETI at Home screensaver. So if you have to divide up that $1 million to 8 million people, you're not going to get rich. If you want to participate in SETI at Home, you can join a team. There's about 60,000 teams. The teams compete with each other. Here's IBM's donated 2,000 years. And this competition has led to some bizarre behavior. Some people build these computer clusters in their basements. Here's a guy who's built a cluster. You can go to this website, setifarm.org. They're all guys, by the way. I don't think any women build these clusters. I don't know why this guy's got his bolt cutters with his SETI cluster. If any of you know the answer, I'd like to talk to you. You can even buy work units on eBay. This guy's done 7,000 work units, and if you win this auction, he'll transfer the work units, these 7,000 pieces of the sky, over to your account, make it look like you've done a lot of work, and your name will go bubble up to the top of the website. The website's very popular, a couple 100,000 visitors every day. One of the things I'm happy about, we haven't found ET, but we have developed this curriculum for kids with the Lawrence Hall of Science. It's a good way to get kids interested in science. A lot of kids are interested in this question, are we alone? That question gets kids interested in biology and evolution and chemistry and astronomy and physics and a little computing. You can learn a lot about SETI because it addresses all these different fields. That project called SETI at Home led to a more general thing that we developed, volunteer computing or distributed computing. And we developed this infrastructure called BOINC, Berkeley Open Infrastructure for Network Computing. And a lot of people use that computing code. It's open source code to do all kinds of computing projects, not just astronomy projects like SETI and Astropulse, but gravity wave projects, looking for planets, doing global warming research, climate modeling. You can use your computer at home now to look for drugs, HIV drugs, cancer drugs, malaria drugs. There's about 100 projects you can choose from, and you can allocate how you want your computer to be used. You can say, I want 10% of my spare computing cycles for SETI and 20% for climate prediction and 30% for gravity waves, and you can pick which projects you want to do, protein folding. The idea is that most of the computing power now is at people's homes. And we built the largest supercomputer on the planet thanks to all the volunteers who run SETI at Home. That led to this thing called thinking at home for things that computers are not good at. Computers are not very good at pattern recognition, especially visual pattern recognition. We launched a spacecraft called Stardust, and we brought it back, and there are little particles that we were collecting out past Jupiter, microscopic particles somewhere in this aerogel foam. And what we did is we put the foam on a microscope, and we took millions of pictures and we sent them out to volunteers around the world. You can take a little training course. It's called the Stardust at Home Project, and you can learn how to find these particles. And if you find one of these microscopic particles that made up the solar system, you get your name on the science paper. And a lot of volunteers have found these particles that we never would have found without them. Anyway, now there's a lot of citizen science projects, including kind of Stardust at Home. There's Galaxy Zoo, a lot of things that you can do with your brain and your eyes, or you can do stuff with your computer. Some of the other things we're doing in SETI, we're looking for optical signals, visible laser signals. We've looked at about 1,000 stars so far. We looked at this is a telescope we use at Lick Observatory, which is on Mount Hamilton near San Jose, looking for these laser signals. We're also using the Keck telescope on Hawaii to look for laser signals. And we're using a telescope. We just started using a telescope on Mount Wilson, looking for infrared signals, laser signals. A new thing that we're just trying this year is to try to intercept radio signals between two planets. The idea is Earth is getting kind of crowded. We may eventually go to Mars, and if we have humans on Mars and humans on Earth, the people on Mars are going to want to talk to the people on Earth, and so there may be radio or laser signals going back and forth. So we now know about other systems, other solar systems where you might have two planets communicating with each other. When they're lined up with Earth, we might be able to intercept that traffic. We call that conjunction SETI, and we're just starting that off now. This is the telescope we use in West Virginia, trying to intercept communication between two distant planets. One of the other spin-offs of SETI is we kind of used a lot of the equipment that we developed for SETI to do other kinds of astronomy projects. We made the first maps of the black hole at the center of the galaxy using equipment that we originally developed for SETI. Using the equipment we developed for SETI, we found a planet made out of solid diamond. We're trying to figure out how to get there. A lot of women ask me about this. We don't know how to get there, but there's a lot of diamond out there. We found the biggest pulsar, most massive pulsar, and it made the theorists kind of squirm. It ruled out a lot of theories. Some of the equipment we did for SETI is now used in brain research, and we're trying to figure out how to control prosthetic arms. But this is kind of we haven't found ET. This is kind of a summary of our data. 30 trillion fruitless tries, but scientists keep searching. So we haven't found ET, but I'm actually optimistic in the long run. This is a plot of all the searches that we've done and other groups have done as a function of frequency and how much of the sky we've covered and how sensitive the search is. And what I want you to notice about this plot is there's a lot of uncovered territory. So if ET's broadcasting at one of these frequencies, we're looking here, but ET might be out here. So there could be radio signals coming right through right here onto Mount Tam, and we'd be looking at the wrong frequency, and we would easily miss them. So I think we've got a long way to go. But the good news is we're working on bigger telescopes. This is a telescope that's being built in China that's even bigger than Arecibo. It's 500 meters across, called the FAST telescope. Eventually, we're going to build this huge thing called the Square Kilometer Array, made out of thousands of telescopes. There's going to be built in South Africa and also one in Australia. And this we're figuring out how to make these dishes here, and it'll be built instead of building a giant telescope. The idea is to make thousands of little telescopes. We think that's actually cheaper than making giant telescopes now. This is a prototype of one of these arrays of thousands of telescopes. The reason I'm optimistic is because, remember, one of the things I said is that SETI is limited by how many frequencies you can listen to. We don't know what frequency or what channel ET might be broadcasting on, so we're going to listen to many channels at once. And the first thing we did was we built a thing that could listen to 100 channels, and then we built a thing that could listen to a few thousand channels, and now we're listening to 5 billion channels all at once. And the capabilities are growing exponentially. So I think even right now, I think we'd be very lucky to find it right now, but I think in the long run, if this trend continues, the computing power keeps better and better, Moore's law continues, eventually we will have be able to do thorough searches. I think right now we're just getting in the game. We're learning how to do this. We'd be lucky, but I think in 30 or 40 years, we'll be able to do thorough searches, and if there are radio or television signals, we'll have a good chance of finding them. This is a plot of computing power as a function of time. And right now, computers are about as smart as a lizard or guppy. But if this trend continues, eventually computers will get as smart as monkeys, or in 30 or 40 years as smart as humans. And then we can do a much better search looking for ET. A couple other things we can do. Let me go back one. This is a thing that the Europeans are thinking about. Maybe NASA's thinking about putting multiple telescopes in space. And if you did this, if you have really big telescopes, you could maybe take a spectrum of the atmosphere of a distant planet, and we could find out what the atmosphere is made of. So if there's oxygen in the atmosphere, we could say, hey, there's photosynthesis going on. We could detect primitive life, trees or plants that make oxygen in the atmosphere. Maybe we could even detect smog in the atmosphere and say, hey, they're burning carbon fuel. Another thing we'll be able to do in maybe 1,000 years is we could make a huge telescope using the sun as a gravitational lens. There's a problem that it focuses way out there beyond Pluto. You'd have to put the camera way out there. But if you could do that, you could read license plates on an extrasolar planet. Don't hold your breath on that. That's going to be a while. So this is kind of, if you've been asleep, this is kind of the final kind of slide. This is all you have to remember. No ET so far. We're still working on it. Finally, wait, 3 more slides before you applaud. Thank you, though. If you want to learn more, here's the website, or you don't have to write this down. Just Google SETI, S-E-T-I, and you'll find it. And there's a kind of fun thing you can watch on the Wonderfest site or on our site called The Great Debate, where I debated this guy. He wore all black, Geoff Marcy, and he said, Dan, you're wasting your time. They're not out there, and you're never going to find them. And I kind of wore all white, and I said, oh, any day now. We just give us another year or two. Except it took us an hour. You can watch this debate. And then we kind of argued why there might be life or why there might not be life and why it might be intelligent or not. Anyway, if you watch the debate, you go to this website, watch the debate, you can vote for who you think won. I hope you'll vote for me. So far I'm winning. I think I'm winning by quite a bit, actually, 2 to 1 or so. I wanted to end with a couple of haikus. So the people that participate in SETI at home, they help us in many ways. Of course, they lend us their computing power, and they built the biggest supercomputer on the planet. We're very grateful to those of you who are running SETI at home. It's really made the search much more powerful, and people continue to upgrade their computers. They buy a new computer every few years, and so we keep getting more and more computing power and being able to do a better job. The other way that people help, they send us money. They help us write the code. It's a big open source project. They help us port it to different kinds of computers. They send us literature. There's a lot of stuff on the website that people send us artwork. Some people send us haikus. And here's a couple. There are thousands of haikus. I'm not going to read you all of them. But Paula Cook, searching for life, answers are revealed about ourselves. And this is the last slide. Dan Seidner, 1 million Earthlings, bounded by optimism, leave their PCs on. So thank you very much. So I think we have time for a few questions. Yeah, I'll try to repeat the questions. Can you, oh, there you got a spotlight going around. Yes, please, in the white. Shout it out, please. What will we do if we do find a signal? So the first thing we have to do is make sure that it's a really interesting signal, because it might be like a graduate student playing a prank on us. That's happened a few times before. The other thing is that we have a big problem looking for radio signals that we don't find extraterrestrial radio signals. We find terrestrial things that are man-made, television, cell phones. You're not supposed to have your cell phone anywhere near the radio telescope, but a lot of people forget. And so we find these signals all the time. So we have to figure out, is it really interesting, or was it just somebody with their cell phone or something like that? So what we first do to kind of see if it's really interesting is we get another telescope to look at it, and we try to use different people and different equipment and different and so if you have 2 telescopes, you can kind of measure its distance, triangulate on it, and you can see it's not just a satellite or some kind of radio pollution from somebody on the Earth. And once we gain some confidence that it's coming from way out in space, from a long ways away, and it's not a satellite or something going over, then we'll make an announcement. And but we might not be sure it's ET. The announcement will probably be, we found something interesting. We don't know what it is. Here are the coordinates in space. Here's the frequency. Might be ET, might be some new astrophysical phenomenon. And then we hope a lot of astronomers will start looking at it. People all over the world will start looking at it and try to figure out what it is. But once we think we found something interesting, we will not keep any information secret. Everything will be made public, and we'll put it on the website, and we'll make it available. Okay. Yeah. Well, I don't own any of the telescopes, but I do get to use them. So we use, I think we have 8 different telescopes around the world, and these are usually built by government agencies. That Arecibo telescope that I showed you, and the Green Bank telescope in West Virginia, those are built by the National Science Foundation, and anybody can use them. You can use them, and it's free to use the telescope. And the way you get to use this telescope is you write, if you have a good idea, you write it down. It's called a proposal, and you say, I'd like to use this telescope. This is how much time I'd like to use it for. This is my idea. And if they like your idea, they'll let you use the telescope. So anybody can use a telescope, and it's free. Well, you're taxpayer. It's your tax dollars. Yeah, so the question is, how do we determine what frequencies are of interest? So that's a really difficult question. We don't know what frequency ET might be broadcasting on. So one of the things we did at the beginning, because we couldn't cover very much frequency range, was we sort of guessed. And we said, well, if ET is going to send a message on purpose, they might pick a frequency that we could guess and they could guess, even though we're not talking to each other. So one of the ideas was hydrogen is the most abundant element in space. And so they might pick the frequency of the hydrogen atom, which is 1.42 gigahertz. And maybe if they pick that frequency, they'd broadcast a message there, because we're listening that, we're studying the universe at that frequency. That's called a magic frequency. Somehow they'd guess it and we guess it. Then we wouldn't have to do searching all over the spectrum. But then somebody said, well, why should you look at hydrogen? Because there's hydrogen interfering with your, it's noisy there because a lot of hydrogen gas. So what about 2 times hydrogen? Somebody else said, well, what about pi times hydrogen? What about E times hydrogen? So there's a lot of these magic frequencies. It's hard to outguess what ET. So what ET might be doing. So the best thing to do is to listen to as many frequencies as you can. And we're not even sure if they'd use radio or lasers or infrared. So we're trying to we think the best strategy is a multiple strategy, looking at as many frequencies as you can, but we can't cover it all. So one idea is to kind of guess what ET might be doing. The other idea is to kind of scan at lots of different frequencies and kind of scan over the spectrum as much as you can. How many frequencies? Unfortunately, there's an infinite number of frequencies in the electromagnetic spectrum. So we're really just scratching the surface. Yeah. Go ahead. Yeah, that's another difficult question. Would they be using frequency modulation, FM or AM, amplitude modulation, or what? How would the signal be encoded? We don't know the answer to that. So that's one of the reasons why we launched the SETI at Home project, because before we launched SETI at Home, we could only look at a couple of different ideas. It would be a very simple kind of signal. With SETI at Home, we can actually look at thousands of different kinds of these schemes. We can look at for FM signals, television signals, drifting signals, pulsing signals. But so we keep adding new ideas to it. Every time somebody says, hey, let's look for this kind of signal, we add that into the screensaver program. But they may be doing something that we haven't thought of yet. So we keep trying to think of new ways. And we're looking at this algorithm now called principal component analysis. It actually can look for any kind of modulation, AM, FM, or anything that we've not even thought of, and it'll just tell you if there's something that's not noise-like. But that takes a huge amount of computing power. We haven't quite figured out how to do that yet, but we're working on that. Tucker, how are we doing for time? Because I know people want to go to the telescopes, and we need to hear from Paul first. Okay. A young hand here. Okay, please. How long has the SETI at Home project been going? Since 1999, and we still haven't found ET. But it's getting better and better, and we're trying new ideas. And so maybe in your lifetime, don't hold your breath, but maybe in your lifetime. So thank you very much.